welcome to Bite-Sized Corrosion. And I do hope that by the end of today's discussion, you're going to feel that you've heard something interesting or learned something new, and you're encouraged to explore further in the field of just getting to know and understanding corrosion a little. Over the past few sessions, we've been considering the impact of contamination of water, and we've taken a bit of a deep dive into the acid mine drainage space to get us going. Professor Anthony Turton has spent several fascinating sessions with us talking about AMD, what it is, why it is such a hot potato, and looking at some of the proactive measures that have been taken by some of the water utilities to try and ensure that the effects of the contamination are considered when they are planning and maintaining their buried infrastructure. Today, I'm thrilled to welcome Kobus Botes from Tecroveer to the microphone. Kobus and I are going to be discussing some of the engineering challenges that he has experienced that have been associated with developing acid mine drainage systems. So a warm welcome, Kobus, and thank you so much for stepping in and joining us today. So Kobus, I understand that you've got first-hand experience in running an acid mine drainage plant actually from years and years ago. Tell us a little bit more.
Yes, I was involved in the first large commercial acid mine drainage or AMD treatment plant that was first commissioned in 2007 in the Witbank area, Emelathleni. It was on coal mine water, similar to the gold AMD that is being treated more recently in the Witwatersrand. The plant was first designed and commissioned, or like I said, in 2007, 2008. I was more involved in the second phase of the plant, in the upgrade that was started in 2009, where we increased the plant capacity from 25 megaliters a day up to 50 megaliters a day, and with about 10 times the acidity in the water to be treated. So yeah, it was quite a challenging couple of years and a very interesting project for me.
It's really interesting, and I guess most of my exposure through the media has been to consider AMD as associated with the gold mining areas in the Witwatersrand. So it's really encouraging to hear that AMD treatment was already being implemented very early on in the coal-producing areas. I want to hear a little bit more about the challenges you faced with the design, but hang on, before we do that, I'm going to ask if you can just run us through what a typical AMD treatment system would look like and how it works, kind of keeping it simple for those of us who aren't very technically minded.
So AMD is generated predominantly in mining works where there's either iron with a combination of other metals or ores being extracted. AMD is generated by the oxidation of pyrite, which is iron sulfide, that comes into contact with oxygen in the air as well as water. And it's usually in old mine workings, etc., where rainwater infiltrates into the mine workings. There's obviously air present, and then the iron sulfide is oxidized to ferric sulfate and sulfuric acid. So essentially, AMD is a diluted stream of sulfuric acid with a whole soup of other metals, cations, anions in among it. And that composition is largely dependent on the type of rock or the ores where the mining is happening. So different areas will generate different fingerprints, shall I say, of AMD. So the AMD treatment plant, obviously the water is very acidic. It contains a lot of metals, dissolved metals, iron, manganese, aluminium, and then a whole range of cations, anions that all make up that particular water body, whether it's underground or above ground. And essentially, for the mining industry, treating AMD is a cost to mining. In a lot of mines where they have to dewater areas to mine, that water, once you extract it out of the ground or out of the workings or whatever, that water has to be treated. You can't just throw it in a river because there's environmental legislation in place, and responsible mining houses, they try to make it their business to mine ethically. And obviously they have to be environmentally compliant and within the law. So the client wanted to look at ways in which the AMD from the coal mines that was around the Witbank area, that they can extract that water and then treat it. There had already been prior test work done just on the neutralization itself, among others at Anglo Mines. So there was a lot of work done up front, and the company, my employer at the time, took it one step further, and we developed a process where you neutralize the AMD and then you further upgrade that to potable water quality. That's essentially where it's going. So from a typical mine area where you have mine impacted water or AMD, that water is pumped or abstracted or decanted or whatever to a central location, goes into a big plastic lined pond. The water, that AMD, has got a pH of about 3. And so it's extremely acidic. It can have acidities of up to 2,000, 2,500 milligrams a liter as calcium carbonate. The main impurities are the high sulfate content, which makes up the dilute sulfuric acid, and then the iron, manganese, and aluminium content in the water, those base metals, and then all the rest that is in among it. So to treat the water, you first need to neutralize all the acidity. So you need to get that pH from, say, 2 to 3. You have to get it up to 7. In other words, you need to destroy that acidity, and you do that with an alkali like lime, calcium hydroxide, or limestone, calcium carbonate, in order to precipitate the metals that you can precipitate from the water. You need to take the pH up to between 9.5 and 10.5. So you do that using lime. And you also aerate the water because you need to oxidize the dissolved iron and manganese in the water. So you have to provide oxygen and an alkali, some residence time for those precipitation reactions to run to their completion as far as they can go. The neutralized effluent is then overflows to a clarifier or a thickener, where you now have to precipitate out the solids or the salts that you have precipitated in that first neutralization step. So that will typically be ferric hydroxide, manganese oxide, or manganese dioxide, and aluminium hydroxide. So you can precipitate those at high pH. Once you have a clear product on the other side, you also get a sludge from that clarifier, which you can dewater further, and you can actually use that to beneficiate, to make other things with. So it's not all a loss. So there's a lot of benefits that you can get from the process as byproducts. Then the water goes from that. It can go through a sand filter or some pre-filtration, ultrafiltration that polishes the water, removes the rest of the solids. You need to drop the pH again to, say, about 7.5. And then you can take that water now through a reverse osmosis membrane to recover potable water. Then the brine or the reject stream from that reverse osmosis, which is now the saline solution, you can take the pH up again using lime again. And at that point, you will precipitate only gypsum, calcium sulfate, and you get another byproduct that is even better than the first sludge that you're getting. That is something else that you can use in the building industry, in cement making, all kinds of things. Once you have precipitated your gypsum, so you have your second stage reactor, a clarifier or a thickener again, and then you drop the pH again, you can take it through another UF membrane and then through another RO, and you recover a little bit more. Then you can even do a third stage on that. So you can do a stage-wise recovery of water. And the HiPro process that was developed, that technology that was developed, we've achieved water recoveries of over 99.5% of the AMD is recovered as potable water. Plus you get some sludges that are then dewatered, and you can do things with that as well. So obviously there's a cost associated with it. It's not cheap, but if you don't have anything else, then that is your go-to. And for the mining industry, for them to keep on mining, they have to treat the byproducts of legacy mining, things that happened years ago, or the company a couple of years ago, whatever the case is. So that is essentially the process, and that is how you treat AMD with a combination of inorganic chemistry and membrane, and you get clean potable water out the other end and some other byproducts.
So it's quite a nice thing, AMD in, drinking water out. You've mentioned a couple of times about the concentration of salts and the fact that we've got acids and alkalis. You also mentioned that you were involved in the design of the plant itself. And so I wondered how you took your very difficult materials, they're not just all raw materials, but your very different process streams into consideration in the design phase? Because that must have influenced your material selection, for example.
Yes, obviously. I mean, it's part of the design side of process engineering. For that process, you obviously have to set up a model that models the behavior of all those different chemical species in your different processes. So you can predict at a certain removal rate of an unwanted component, that resulting stream will have less of that, more of that, whatever. So you model your whole process, and then you have particular water fingerprints, really, almost a different class of water in each little process step or each little unit operation, that you then have to match your material of construction to the water in that stage. So it's really understanding the chemistry to be able to select the right materials. Otherwise, you can get it wrong. You can still get it wrong, but it depends on how good your model is, obviously.
From my perspective, material selection is always something that I've been fascinated by, and I've done no metallurgy myself, so I'm always bemused by you guys. And when you were doing these designs, were you looking at some of these super fancy steels, or were you able to focus on the use of, shall I say, a conventional stainless steel, maybe with an additional layer of protection added to them from a corrosion perspective?
Obviously, it's a trade-off between cost and functionality. So, as I said, when you develop your water quality model for your different unit operations, you need to match your materials to the worst water quality that you can expect in a certain area or in a certain unit operation. So you have to understand the overall inorganic chemistry of what that water does, or what it's going to do to your different materials in a particular area. You have to match the materials to the different conditions that you encounter in the different areas.
And I presume that steel isn't your only material of construction. You obviously have some concrete components.
Yes, in terms of corrosion, if you talk about corrosion, metal corrosion, steel corrosion, that kind of thing is predominantly driven by chlorides, by the chloride content in water. So, for instance, if you have a chloride content of less than, say, 100 milligrams a liter, you can use 304 stainless. If it goes up to 1,000 or less than 1,000, you can use 316. If it goes over that, you have to go with duplex stainless steels, very expensive construction materials. So you have to match your water quality, because you have all these very corrosive process streams, and depending on what you build your plant from, if it's a big plant like a 25 or a 50 megaliter a day plant, you would typically build your big structures, reactors, clarifiers, thickeners, that kind of thing, you will build in concrete. So, but concrete is also prone to corrosion. So there, it's the sulfates that become the issue, because the sulfates, once they penetrate into the concrete and you get your saline solution into the concrete, then you start corroding the rebar. So you need to protect the rebar by using protective coatings on the concrete, because they are also affected by the water quality in these different process unit operations. So it's not only steel. You have to look at your whole plant, and you have to design and protect each structure or each piece of equipment according to what is it going to be exposed to. And yes, it's not only steel, it's concrete, it's anything associated with that plant.
And I can imagine it's easy to consider and design for a single tank or a single clarifier. But when you're talking about a process, you're going to have multiple storage tanks, clarifiers, settlers, filters, and so on. And each of those needs to be considered. And this is a bit of a nasty question, but in the design, given that you were involved really early on, and I want to say groundbreaking, so didn't have all the necessary information, did you find that your design was adequate, or did you have failures? And you can pass the question if you don't want to answer it.
Yes, the technology was quite on the forefront of AMD at the time when the process was developed. And the design team had to be very conservative in our design approach, because you can design, or according to your understanding, you can do the best design, but things happen and everybody makes mistakes. So we were initially very conservative, but also you're working with budget constraints. So you again have to balance fit for purpose with what you can afford or what the project can afford. For instance, in the Mlatleni project, in the first phase, in the stage one clarifiers, where you do that first precipitation of the metal salts. We went with rubber-lined carbon steel because at the time it was deemed a cost-effective way to protect those that internals of the clarifiers. And I mean, that's the shafts, the rakes, the sludge domes, all the internals, all the wetted internals of the clarifier. And those were originally, certain portions of it was done in stainless steel, certain portions of it was done due to cost considerations in rubber-lined carbon steel. In the phase 2 project, or during the operation of the first phase, testing was done and we found sulfate reducing bacteria, and we found corrosion issues that we had not anticipated, because you don't expect anything to live in that acid, but it does. During the second phase of the project that I was involved in, we then changed those first phase equipment, those wetted parts, we changed out to 316 stainless, because in the second phase, we had money allocated in the project to take care of that. In the membrane cleaning areas, the CIP areas, cleaning in place where you make up your cleaning solution to clean the membranes that you use in the water recovery. We use, for instance, initially galvanized steel in pipe supports, in that kind of structural steel around tanks and pumps and whatever. Also line the concrete, but you anticipate, but you can't predict. So eventually when it happens, then you find, well, it doesn't work. Then we had to replace all of those with go to non-corrosive. So the cheapest at the time was either go to epoxy coat galvanized steel so that you protect it further, or you go to other construction materials like GRP, which you can use as structural members, etc., in very high corrosive areas. So then you change to what is best suited for that particular application. We had concrete chemical attack due to the extreme process conditions. Like I said earlier, you get corrosion of the concrete itself at the high pHs and the salinities, etc. Then you have to protect those structures with suitable chemical coatings, which obviously have to be applied in the correct manner, and you have to follow the procedures, and sometimes you get coating failures as a result of something that you didn't anticipate, or the application was poor, or the contractor who put it on didn't do the right job. Anything can happen, but that's the kind of thing, you get a lot of challenges that you have to overcome in the design and in the implementation of that project, and then you find you got it wrong, and then you have to fix it, and hopefully you have money to do it, so or the client does rather.
Well, it's actually wonderful. Thank you for sharing so honestly, because there can be this tendency that, it was all perfect. And I think we all deep down know that probably wasn't the case. So thank you. But thank you for sharing with us a story that's successful of AMD reclamation being implemented successfully and potable water being generated at the end of it. You mentioned right at the start that this was in the coal sector, and much of our discussions prior to this were related with the gold mining areas here in the Witwatersrand. I believe that AMD processes have been implemented around here. Are they also learning from your mistakes and having relatively trouble-free implementations?
Yes, Tecroveer was involved in 2 big AMD plants in Joburg. The one is Central Basin treatment plant, which can treat up to just over 80 megaliters a day of, or neutralize and settle, clarify, and discharge up to 80 megaliters a day. And then the Eastern Basin plant, which can do over 100 megaliters a day. So in total, there's like 200 megaliters a day of water that's being pumped continuously every day, neutralized, treated, and then discharged. If you can take that a step further, then you can add a membrane section at the back of it, and you can make that water potable. But obviously, there's a cost involved. So Tecroveer was involved in the 2 plants primarily on the thickeners, where the settling of the sludges that are generated by the process, where they are settled. And Tecroveer did the design and the implementation of those clarify or thickener internals. A couple of learnings that were experienced along the way. We had issues with galvanic action between 3CR12 and 304 stainless, where the 3CR12 over time completely disappeared, and we had to change the materials. There was construction errors on galvanized bolts, mild steel washers, etc. There was an air release on a thickener feed line that was spraying saline water all over a galvanized steel bridge that was sitting over the thickener, and that started corrosion on
And it's
those
not
parts.
sitting there
Obviously,
anymore. Yes.
yes. To rectify it, we had to move the spray out of the way so that it's not in an area where it's going to hit anything that is going to corrode. And obviously we had to do repair work on the galvanizing on the bridge. So yeah, you learn as you go along. You get it wrong sometimes, but we learn and we get better.
Well, I think that getting better is the important thing. And while it's scary that corrosion can function as a magician, kind of now you see it, oops, now you don't, that's not really what we want. And it's lovely to hear that as you're learning, especially I think the challenge of using different materials in the same area of a plant or a structure, which can really cause problems from a galvanic corrosion perspective. And it's encouraging to hear that as you're learning and implementing and then thinking in a new application how to double check yourselves in that regard.
As in all other process plants, taking care in your material selection during the design phase of AMD treatment plants, like anything else, can really make a difference considering design life of these plants that have to be 20 years or more. So you want to protect your assets and you don't want to spend additional money on having to repair things that are supposed to stand there for 20 years. So yeah, each mistake we make, hopefully it helps us to gain some wisdom, to learn, to get experience and impart that knowledge and pass it on so that the younger engineers or the next generation do not make the same mistakes as we did. It's all part of the continuous improvement process engineering, I suppose.
Well, thank you for sharing some of the challenges that you have experienced and how we can all learn from that and put into practice better design principles. And thank you too for stepping in to give us this very interesting perspective. And I'm really sure that all the engineers will take away the value of thinking not only about the big structures, but also about the little ones. And really that it's the small tanks, the nuts and bolts genuinely that need to be considered to make sure that corrosion is conquered.